So in this presentation, now that we have understood how to capture or calculate sigma, let's look into how sigma connects to the idea of distributions. Before we look into how sigma is related to a distribution, let's start understanding the bells and whistles of a distribution first. So what is a distribution? In its simplest terms, a distribution is a representation of a data set that showcases the count of data points in that data set. Count is also called frequency. So in other words, the distribution is essentially visually representing the data set with the frequency of data points in that data set. Okay, so if I have a set of males and females, let's say, in a class, okay, and so let's say we have 3 males and 4 females. The way we would represent that is three males and 4 females here. So if you really think about it this way, this is your males, these are your females, right? And that's the basic representation of the distribution. This is the frequency of males and females as you see in the chart. Okay, if I add another male to it, it suddenly becomes like this. Both males and females are present in the same number. That same thing can be said of numerical data. Okay, this is categorical data, but with numerical data you can do the same exact thing. In certain cases you create something called histograms. Okay, but these are all frequency distributions. What you are seeing here for each of these towers is the frequency of that specific groups present. Okay, so if this is between 0 to 2, 4, 6, 8, 10, 12. So I can say that the 2 to 4 group and the 6 to 8 group has the highest frequency of occurrence among the others. Okay, so that's the idea of a distribution. Now, when it comes to a continuous variable, the one that you have learned in 612 is more commonly called a bell-shaped curve or a normal distribution. So here, instead of discrete values, I have a set of continuous values, which basically means that the variable can take any value between this point and this point. So for a continuous distribution, it is still the same idea. Okay, so your maximum frequency is basically here, right? And that corresponds to your mean. Because the specific number, which is turning out to be your mean, comes across in the data set the maximum number of times. That's why it is the mean. And the rest of the distribution is equally distributed as it tapers down on both sides. And so it makes it a symmetrical distribution. That's basically what this bell-shaped distribution is. I'll give you a simple example that will hopefully illustrate the idea of this mean. So just for the next 15 seconds, follow along with exactly what I say. Okay, as you're listening, I'm going to blabber a bunch of numbers. And I want you to put one ear to what I say and the other ear and the rest of your mind on something else. This is a perfect time for you to, let's say, open up your cell phone, check your mails, go into social media, and do something else, even while keeping one ear ready to listen to what Dr. B is saying. Okay? Don't listen to it too intensely. Just keep it in the rear view mirror. You guys ready? Open up your cell phones. Very good. Start working. Now, I start. 2, 4, 5, 4, 7, 6, 4, 4, 4, 3, 4, 3, 2, 3, 4, 4, 5, 4, 6, 4, 7, 6, 4, 4. I stop. Okay, now put away your cell phones and come back to me. If I ask you that I just said a bunch of numbers, what's the possible average of those numbers? You look at me probably as if I am from Mars and says, Dr. B, I had absolutely no clue of following along with you. You just blabbered a bunch of numbers. But oh, wait a minute. If I recall correctly, the one number that you said the most number of times was 4. And so I'll just make one wild guess that the average of that set of numbers that you just blabbered is 4. And lo and behold, you'll find in reality, if I go back to those numbers, and I personally don't remember what I just said, but if I add them up and divide by the number of elements, the answer will come as close to 4 as possible. That's the whole idea of the maximum frequency in the data set being the mean. So that is how any distribution is designed. That said, I want to talk about 3 specific properties of a distribution, and this is across the board. Doesn't matter if you are looking at a uniform distribution or you are looking at a discrete distribution or you are looking at a bell-shaped curve. Okay, irrespective of what you are looking at, these are the guiding angels, and I want you guys to follow this very closely. Okay, so the first one is this line here. Okay, the x-axis. That is the first piece of the puzzle. A, the x-axis defines what? You want to very clearly understand that. The x-axis defines data. End of story. Okay, so this can be a normal distribution of grades. Then this x-axis defines grades. You are showcasing the normal distribution for grades. If this is about stock prices, then the x-axis defines stock prices. If this is about age of people, then this x-axis defines age. Okay, in all these cases, here it was sex, if you recall, males and females. Okay, it can be a uniform distribution. The only difference between this guy and this guy is, for the uniform distribution, your output across the board is the same, which makes it uniform. Here the output is different. You have a mean that takes over the central piece, the central tendency, and then the frequency tapers down on either ends. So one more time, the first property of the distribution is your x-axis. What is it representing? It is always representing the raw data. Now, let's look into your y-axis. What is this line representing? What are these representing? And in this case, what is this guy representing? Again, they are all doing the same exact thing. That is representing something that we define as frequency. One final thing that I want to tell you is, while you are on that x-axis, always realize that you are going this direction in your measure. In other words, this is your mean. This point here is always capturing the minimum value in the data set, and this point here is always capturing the maximum value in the data set. It's the same story from minimum till maximum when you are looking at a continuous distribution. Discrete, it's a different story because you are looking into 2 discrete kinds of data points, males and females. It's the same thing that has been measured on your y-axis. It's still frequency. Okay, So far we have looked into two properties. The first is the x-axis measures or represents the raw data, and it goes from a minimum to a maximum, from a left to a right, with the mean in the center for continuous data. The y-axis, in whatever shape it is or form it is always measuring frequency. Okay? And last but not the least is this area under the curve. This area under the curve, which is your third property, is measuring probability, or your chance of occurrence, your overall proportion. What is the total probability of having all the values between a minimum value and a maximum value? You guessed it right, it's 100%. If the mean is a central location and it divides this area into two equal halves, how much are each of these areas? 50% and 50%. That's it, guys. Three important properties. The x-axis is always representing the raw data. You go from left to right, from minimum to maximum, with the mean in the center for continuous data. The y-axis represents frequency. And the area in the curve represents probability. It's the same story for this as well, especially when it comes to continuous data. So with that backdrop, let's look into the idea of continuous random variables. So a continuous variable x takes all values in the interval, which basically means that it can take in as many possible values as it can between this min and the max value. How do we assign chances to events in a sample space? If this is your sample space, 100%, how do you assign your chances? We use density curves and compute chances for intervals. Okay, the chance, or the probability in this case, is the area under the density curve for the values of x that make up the event. So here is a perfect example. This is a simple uniform distribution, okay, for x that takes values between 0 and 1. And you have the height, which is constant at 1, which makes this a uniform distribution. So if I ask you the probability that x falls between 0.3 and 0.7, the probability that x takes a value, so this is your x, right? That's your data. The probability it takes a value between 0.3 and 0.7 is essentially this entire area under the curve, right? And this is an easy fix because you're looking at a rectangle, and therefore this is your height, this is your width. The width is 0.7 minus 0.3, which is 0.4. The height is 1, and so the area of the rectangle turns out to be 0.4. Very, very important, and this is a conceptual issue. In a continuous distribution, you cannot find the probability of a single event. At any point of time, if I'm trying to find the probability of x being equal to 1, I don't have a height to play with. No, my height is 1, but I don't have a width to play with, sorry. It has to have extremes within the width from one point to another that it can measure. And it's the same story for continuous distributions like the bell-shaped curve. It's the same story. The shaded area under a density curve shows the proportion or percent of individuals that fall between those values of x1 and x2. Because the probability of drawing one individual at random depends on the frequency of this type of individual in the population, the probability is also your shaded area. That is the probability that the data set, the data point x, will take a value between x1 and x2. So with that said and done, how in the world does the idea of sigma that we have discussed in the previous video fit with this discussion? So let me give you an example. Okay, imagine that these are three possible outcomes of your grade in my class. Okay, and I'm going to draw distributions for each of these. Okay, imagine the average grade in this class will be 80. Okay, and it is the same average in all these three scenarios. However, for the first scenario, my distribution is something like this. For the second scenario, my distribution is something like this. For the third scenario, my distribution is something like this. Which one, as an educator, will I be happy with? 1, 2, or 3? Ask yourself that question. They all have the same mean. The mean is still 80. But when I put the entire data set, which is all your grades, into a distribution, the distribution gives me the frequency, and imagine I have 3 possible ones. When all of this is done and dusted, when I go back after teaching this class, which one would I go back with a happy face, knowing that, okay, I've done my part? You got it right. It's this guy. Why? Because here my data points are very close to the mean. They are shrunk closer to the mean. The biggest difference between these three pictures that you see is the spread around the mean. And oh, by the way, what did we call that thing? Variability, or sigma, right? Sigma is a measure of the spread in the data set. Spread around what? Spread around the mean. The more spread the data set is, the harder it is to make decisions. So as an example, in the third case, okay, you have a mean of 80, but it is a very, very wide spread. So it's highly possible that this guy here scores 100, but there is also another student in this class who scores a 20. What do I get out of this kind of an output? What do I tell myself? How well did I teach? Good, bad, ugly? I have absolutely no way of figuring it out. Guess what happens here? The highest score is probably somewhere around an 85. The lowest score is somewhere around a 65. I can live with that as an educator. I can actually make judgment calls out of it that, okay, overall, the students have learned it right and learned it together in a very similar way. If only I could have moved this entire curve to the right and increased my overall mean, that would have been so much better in terms of learning. But overall, I can at least make some judgment calls from this. I have absolutely nothing to make from here. This is very mediocre, but this is the one that I'm looking for. So that's the idea of spread. If this one has a sigma of sigma 1, this one has a sigma of sigma 2, and this one has a sigma of sigma 3, which one is the highest? Sigma 1, sigma 2, or sigma 3? One more time. Remember, sigma is a measure of spread. Again, you got it right, because this specific curve has the highest spread. It also creates the maximum value for this sigma 3. This one has the lowest spread, and therefore the corresponding sigma 2 value is the minimum value. And so oftentimes you can start with a class that has this kind of a characteristic, and your job is to try and convert that sigma 1 to a sigma 2. In other words, try to move from this kind of a curve to a curve that is much more closer to the mean. What did you do in the process? You are improving variability. You are improving sigma. So what have we done so far? We have talked about what we are measuring. How can you measure sigma? And then we are looking into pictorially how sigma fits into a distribution, because now we can start figuring out how we can reduce this sigma. Okay, what needs to be done to go from here to here is what operations management will teach you. But this is the underlying idea of how you want to reduce sigma. In the next video, we'll talk about sigma and the empirical rule and gradually give you an overview of Z.